Okay, so our last question today is we're going to look at the elevator problem. So this is a very good one because it makes sure that we understand how net force works in free body diagrams. Some of you may have done this in grade 11, but if not, follow along. So this question is saying how much does the person weigh? So normally it has a mass of 85 kilograms, where mass and weight are two different things. Mass is based on how much stuff, how many particles the person is made up of, or weight is dependent on the acceleration due to gravity. And if you're on the Earth, your weight is different than if you're on the moon. But also we have what's called apparent weight. If we are accelerating, you can either feel moments like weightlessness, or you might feel lighter or heavier depending on if you're accelerating downwards or upwards. So looking for the apparent weight as we accelerate. So for those of you that have been on like a roller coaster, you know that when you're rounding the top of a curve on a roller coaster, you feel that moment of weightlessness. Where you're rounding the bottom of a curve, you feel yourself, it's as if you're being pressed down into your seat. You feel heavier. Your mass hasn't changed, but you feel heavier or lighter. So the first one is, what happens when the elevator is stationary? This is the same as thinking or at a constant velocity. Because for both these scenarios, one, you're traveling at constant velocity, which is the same as when you're stationary. This means that your acceleration is 0. Let's draw a free body diagram. Here is some elevator. If you want, we can draw a person inside the elevator. So we ask ourselves, what forces are acting on this person? So first we need to recognize that A is equal to 0 meters per second squared when we are stationary. So what that means is that if A is 0, that must mean that the sum of our forces must also equal to 0. That means all the forces up must be the same magnitude as the forces down. So we draw some force on this. I know there's force of gravity acting downwards, but there's something preventing us from falling through the ground, and that's our normal force. A normal force going upwards. And the two arrows I drew should be relatively the same length because our net force is 0. The upwards force must equal the downwards force. So if I look at some of the forces in the y direction, we can see that the normal force minus the force of gravity. Well, we just said that the net force must be 0. So you get 0 is equal to Fn minus Fg. So we can see as normal force is equal to the force of gravity. So when we are traveling at constant speed, or that's also when we are stationary, our weight is as we normally feel. Their Fn is just going to equal to mass times gravity, which is 85 kilograms times 9.8. And we get around 830 newtons. Now for this next one, it says, what happens when the elevator is accelerating upwards at 2.3 meters per second squared? So are we going to feel heavier or lighter? So hopefully you've actually experienced this, and you can actually you kind of know in advance, like, oh, I expect a greater force because it's accelerating upwards. If not, we can go ahead with the calculations and see what happens. So for this one, we know our acceleration is upwards, so positive 2.3 meters per second squared. So what this means is that our net force must be bigger in the up direction. Because the only way for us to accelerate, the unbalanced force must be in the direction of the acceleration. So if I draw this free body diagram, our force of gravity technically hasn't changed. We're still just 85 kilograms on Earth, but now it must mean that our normal force is going to be bigger. So you see, some of the forces in the y direction is equal to mass times acceleration, which is equal to Fn minus Fg. This time ma does not go to 0 because our acceleration is not 0. So we're looking for apparent weight, that's Fn. So we solve for Fn. Fn is equal to ma plus Fg. So we can keep simplifying this. So we get ma, Fg is just mass times gravity. So So you can see that Fn is just going to be mass times A plus G. So if we're accelerating upwards at 2.3, just add that to the 9.8, multiply by our mass, we get a value of Fn is equal to 1.0 times 10 to the 3 newtons. So around 1,000 newtons. Lastly, what happens when we're accelerating downwards? Well, from the previous one, we saw we added the acceleration of gravity. Gonna make a guess, we're probably going to be subtracting. So in this case, A is equal to negative 2.3 meters per second squared, or we think of it as A is 2.3 meters per second squared down. Okay, so Fg is still the same. Fg is still, like, force of gravity didn't change, so notice how I'm just drawing my force of gravity vector the same length each time. However, in this case, our normal force must be getting smaller. So in this case, we have sum of the forces in the y direction is equal to ma, and that is equal to, in this case, so there's two ways we can approach this. If we define up as positive for these ones, and continue as I am, but I like to think of the direction of motion as the positive direction. So I'm actually going to say down is positive for this one. So I'm already taking into account directions. So down is positive, I'm going to end up with Fg minus Fn. So if down is positive, that means my acceleration is positive in downwards direction. Fg is positive in downwards direction. Fn is opposing that acceleration. So that is Fn. Okay, so then we have solving for Fn again. Fn is equal to Fg minus ma. So we get Fn is equal to mg minus ma. We have Fn is equal to mg minus a. And when it's all said and done, plug it in, we get Fn is equal to 640 newtons.